So, hello everybody. Welcome to another green energy series. This one is about Passive House, and we're gonna get it's sort of a Passive House 101 course, and we're gonna talk about the basics of Passive House in this presentation. So, this presentation is through Solar Oregon. Solar Oregon has been around for 46 years as being a cornerstone nonprofit in Oregon, doing education, outreach, and community advocacy work around solar. Um, the Solar Oregon does many how to go solar plus storage webinars. These are sort of if you're not familiar with solar or solar plus storage, it's like a 101 presentation, and these 101 presentations are given approximately once a month. So if you want to kind of look at that presentation, you're welcome to join one. The Yeah, if when they are offered, is you can find them on Eventbrite. So if you search Solar Oregon on Eventbrite, you can find the future offerings of the How to Go Solar Plus Storage a webinar. And then Solar Oregon also organizes solar tours. In the picture to the right, you see that there's a tour that was organized to look at commercial PV systems that are installed in on farmland to do agrivoltaics, where some farmers have found really great synergy where bifacial panels that are semi-transparent are installed over top crops, and those crops don't get sunburnt because the solar panel is shading them, and the crop also requires a lot less watering, and so you get water savings, but then there's still enough sun for the crop to result in very good production and yields. And so, really great tour. Additional solar tours will be announced, and you can also check your email and look at Eventbrite for any uh, scheduled solar tours that are up and coming. Um, we also do solarized campaigns where we canvass neighborhoods to organize many homes in a particular region and connect them with solar contractors. And so then, that neighborhood can do a bulk buy for solar panels and inverters and really kind of organize the installation of solar, rooftop solar, and result in some economies of scale and savings. And then we also do many peer-to-peer education events, such as this Green Energy Series. So if any of that work sounds really cool to you, you can support our work by looking at going to this website and giving us some donations. Um, we have a very small staff, two paid staff. Everyone else who does work for Solar Oregon are volunteers, including myself. And you're encouraged to use the Zoom Q&A features to ask questions, and I'll check the Q&A after the webinar and answer as many of the questions as I can. So, my name is Edward Louie. During my day job, I work as a building energy efficiency research engineer at Pacific Northwest National Laboratory. PNNL is one of 17 national laboratories that are mostly funded by the U.S. Department of Energy. And I love my work, and so much so that even on a Saturday, I've prepared presentations such as this Green Energy series to talk more about energy efficiency in buildings. Um, you can also find me on LinkedIn, and I frequently post on LinkedIn about, things that pop into my mind about energy efficiency that are worth discussing, or interesting tidbits that um, uh, could be interesting to you. A disclaimer is that The views in this presentation don't necessarily represent the position of Pacific Northwest National Laboratory, the U.S. Department of Energy, or Solar Oregon. Best efforts have been made to convey facts and information accurately. However, you're encouraged to do your own research before making any investment decisions. So with that, let's kind of look into the overview of this Passive House Basics presentation. So we're going to start off really looking at answering the question of what is Passive House. Then we're going to answer the next logical question, which is why Passive House. And then we're going to look at the history of this standard. Then we're going to look at Passive House principles and some of the benefits that come out of these principles, including thermal comfort and satisfaction of living in the home and reduced risk for damage due to moisture. Also, improved resiliency to power outages during extreme heat and cold events. We'll also look at how this Passive House standard has evolved over time and look at kind of the different flavors of Passive House that have branched out. And then we're going to come to some conclusions about some general approaches to retrofitting an existing home towards Passive House, and also look at some conclusions. So let's kind of answer the first question, what is Passive House? And as I alluded to, it's a set of definitions that a home needs to fulfill. So you can call them standards. So it's clearly defined standards that a home or building that must fulfill in order to achieve the different kind of flavors of Passive House, whether it be PHI's Passive House, EnerPHit, which is a PHI standard for retrofit. PHI also has a low energy buildings standard. And then PHIUS, another branch of this Passive House. So Passive House became two organizations. One is PHI and the other one's PHIUS. And they each kind of run their standards. They're more similar than they are different. But PHIUS has a standard called Core, and they also have a PHIUS Zero standard. And we're going to later get into kind of the nuanced differences in these different standards. But regardless of whether a home is certified through PHI or PHIUS, the standard process involves both a it starts with consulting. So like if you work with a certified professional, they will kind of guide you through the design process, look at your blueprints and your plans in the case of retrofit, and give you some advice on what to do and any changes that to be made. But then throughout the building process, this qualified professional will continue to inspect the building, and then at certain stages will be involved in testing your building. And so in the end, only a building that's proven to actually achieve and perform the required standards receive a certification. So it's not a check the box, I've got it, type standard. It's very much a performance-based standard, which is very different than some of the other above code energy efficiency programs that are out there, where it's much more of a assets checklist approach. This one is very much the opposite of that, which is performance-based. So then, why Passive House? Well, Passive House is a very stringent standard that results in a home that is very, very energy efficient. But in addition to that, it accounts for looking at window orientation and glazing to understand whether the home will, because it's so well insulated, results in overheating during the summertime. And so there's also metrics for thermal comfort. And so it's not just pure throw as much insulation into the walls and roof as possible, but the standard also has requirements for the number of hours that the home must stay within a temperature bound. So then that's to really understand thermal comforts. Um, and but because it is super, the standard requires the homes to be very well insulated and air sealed, then it also results in the home kind of being like a Yeti cooler, which stays at the defined temperature for many hours. And so Passive House may be of an interest to someone. Also, if you're interested in having a home that remains comfortable for many hours during a power outage. So, like last January, when many people in Portland lost power for many hours, I know I lost power for about 30 hours. And during that time, I was really hoping that, the power would come on sooner because, my house could not maintain temperature at comfortable temperatures for that many hours. But later in the presentation, you'll see just how different Passive House performs during a power outage in winter compared to other homes. Passive House is also because of how airtight the home is, wildfire smoke doesn't creep into the home. And so as a result, healthy indoor air can be maintained during a wildfire. Passive House also has requirements for mechanical ventilation that is very good, and so that means the mechanical ventilation system has to have high filtration levels, and so then that also helpful for like wildfire smoke, if that's um, another advantage to Passive House. Um, and then uh, also that there's requirements for insulation and the insulation to be placed in a way that results in building materials to not reach dew point. And so then that really helps with the uh, durability of those building materials. And when building materials don't are set up in a way that um, where moisture is not going to degrade them, then they'll last a very long time, and that really reduces long-term maintenance cost of the building. And so there are many kind of angles and uh, reasons why someone would be interested in Passive House. And uh, I think as we experience more of like extreme heats and cold events and power outages, people are now looking to Passive House more so beyond just, oh, well, it saves money on utility bills, which we also have currently recently experienced rapidly rising energy costs. And so that's another reason why in the past, there may have been less interest in Passive House, but now having a home that is extremely energy efficient and has on-site renewable energy generation to kind of be resilient to rising energy costs. That's another really interesting and desirable feature that's driving a lot of interest to this Passive House standard. So this history of Passive House is also related to energy cost spikes. In the 1970s, when there was an OPEC oil embargo, um, a small number of builders in North America started to think about how to build homes that use little to no energy, but would not result in the overheating that homes that were so-called passive solar designed in the 1930s experienced. And so in the 1970s, these builders built some example homes. There's two of them in the center images. Um, as you can see, these homes are quite simple looking. They don't have crazy roof designs. And so by product of the home being kind of simple, they were able to use the technology of the time to design a home that used very little energy and really achieved their goals. Now, then in 1988, two people, uh, Wolfgang Feist and Bo Adamson, they started looking at, okay, codifying these concepts and principles together so that to create a standard. And so, that sort of thinking led up to 1996 when the Passive House Institute was founded and releasing the first, official standard for Passive House. Um, and Passive House Institute had its beginnings in Germany. So in the U.S., Passive House Institute, U.S., which shortly named FIAS, wanted a kind of originally it was a subchapter of PHI, but then in later, past 2007, like I think it's like 2013, became kind of independent. But in 2007, it was actually operating under PHI. And so that's kind of the history of the Passive House standards in terms of how it was organizationally structured. So as we were talking about, the Passive House is a set of standard building the standards. Um, so let's kind of look at some of the principles that are kind of the pillars of the Passive House standard. One of them is high performance windows, and the reason for this is that windows are a thermal hole in the wall. Um, and this is true even if the window is shut. So if you, and we'll see this later in later slides, but like some good practices is to pick the highest performance window you can afford, and that typically means a triple pane window. And FIAS actually has a window database of windows that generally qualify for being used in a um, passive house designed home, and these are the windows that make this list are ones that have not only just high performance glazing but high performance frames as well, because as you'll see later, trying to nab these thermal bridges is really important. So like if you have, it's kind of like a bucket. It doesn't matter how waterproof the actual material of the bucket is. If you have even one hole, all the water leaks out through that hole. And so in a window, if you have really well insulated glass, but then you have a sucky window frame, then all the heat actually escapes not through the glass, but through the frame. And vice versa. If you have a really good frame, but crappy glass, the same happens there. And another thing to be really thoughtful about is it's not just important to, pick a good window, but the design of the transition from the window to the wall and ensuring that there's no thermal bridges or trying to minimize those thermal bridges between the rough opening and the window is also really important. Um, and in the passive house energy raters uh, are very careful to consider this detail, um, which other energy modelers who are not passive house professionals may just gloss over. But those who are involved in the energy modeling of passive houses are very particular about this detail, and it's because there's so much heat that gets lost or gained through those thermal bridges around windows. And so here's some like example calculations. And so like if you have a 8 foot tall, 25-foot wide wall, and the cavities of this stud frame wall is insulated of R21, which is a typical insulation you can put into a 2x6 wall. And if you had these size windows and the windows had a U value of 0.35, your total wall R value average is actually nowhere close to being 21. It's 8.2. So it's pretty bad. And the reason why is because that R value is significantly dragged down by these windows that are 0.35. Now, if you take that same wall and you put in much better windows, 0.11 windows, code right now is a 0.3 window. and so these are almost three times as good as code. Then finally you get a wall that's R13 and a half. Um, so that's still not R21, but it's a heck of a lot better than 8. Um, so one kind of thought experiment you can have is, okay, well, if instead of making the wall have better windows, if you just stuck with code windows and just thickened the wall up, made the walls thicker, um, how thick would the wall need to be in order to actually get R13 and a half? Well, it turns out that the wall needs to be freaking crazy thick. As thick as a Hummer is wide. Um, and nobody will build a wall that thick. So this is just an example of why it's so important to have better performance windows, because trying to make up for the crappy windows with thicker walls is just, not feasible. Now, another thought experiment is, okay, well, what if you needed the windows, uh, like what level of wall thickness would you need in order to get R21 if you with code level windows? And the answer is, like, it's impossible. So, um, anyways, uh, hence why these thought experiments really, I think, hammers home why it's important to have good windows, and why Passive House, one of the principles is to have, high performance windows. Another Passive House principle is to have um, the continuous fresh air, controlled fresh air. So in drafty homes, the air exchange to get fresh air is uncontrolled. Like, you get a lot of fresh air on a windy day when, the air from the outside is coming through the cracks in the wall and the windows and stuff. But then on a mild day that where the temperature outside is not that different from inside, and there's no wind, you basically have no air exchange. And so neither is a good strategy. You don't want excess air exchange, and you certainly um, would. It would be better if the air exchange was involved some energy recovery. And so Passive House requires mechanical ventilation, and really, really, in order to hit the energy requirements of Passive House, you basically need to have energy recovery ventilation. And so, how energy recovery ventilation works is that um, the outgoing air in the wintertime um, is warm air, and the outside air coming in is cold. And so, in this heat recovery core, um, there's a bunch of layers of plastic that are, at right angles to each other. And this kind of plastic, when you hold it in your hand, it looks like kind of like those um, uh, campaign yard signs, that type of plastic that is used to make those campaign yard signs. Um, this corrugated plastic, and they stack a lot of them, in right angles to each other, and the air flowing from one direction is so close to the air flowing the other direction. The air actually never mixes. It's just that there's so much surface area from the air touching each other through these different corrugated plastic layers that you get this heat exchange. And so um, in the wintertime, the heat escaping it preheats the cold air coming in. And in the summertime, the reverse is true, that cold air conditioned air is pre-cooling the hot, fresh air coming in. Um, Now, these energy recovery ventilation devices, um, they they sell them at different CFMs, and typically, you'll find that when they're sold, they're advertised as their maximum CFM that they can produce. Now, the problem at max CFM is that the actual energy recovery percent is really low, and so um, if you're trying to build a passive house, or in any case, any home that you want mechanical ventilation, um, and you're interested in maximizing the amount of energy recovery you get out of your ventilation system, what you want to do is actually look at what the CFM is at the max sensible recovery rate, or SRE. And so Um, it's kind of hard to find this kind of information at different manufacturers' websites. And so there's a website called Home Ventilation Institute, HVI, and there's a certified product directory you can download as an Excel file. And then you can actually filter by the sensible recovery rate. Um, you can also filter by the CFM of the product, and then that will really help shorten your list to pick out uh, a product that an ERV that has the high, a high enough sense of recovery to kind of meet your requirements. Um, Currently, the 2021 residential code gives you a point. So, how the energy code works in the 2001 IRC is you get to choose from like a list of like 6 or 7 options. You get to choose like one or two, and one of them is ventilation that has a 75% sensible recovery or higher. And so then you can go to the HVI database and search for and filter for energy recovery ventilation devices that have a 75% or higher sensible recovery, and then drill down to then look at the CFM you need based on your ASHRAE 62.2 calculations. So passive house mechanical ventilation that involves energy recovery is another principle. These units, they also sell them. Typically, they come with like a MERV 4 or MERV 8 filter, but you can buy upgrade filters that can typically go up to like MERV 13 or higher, and so that's also really good for filtering out wildfire smoke and uh, vehicle pollution, and so that you can get really high quality filtered air through your mechanical ventilation system. Another passive house principle is very good insulation. Um, Now, the insulation levels for to meet passive house standard has been toned down a little bit in particularly hot and temperate um, climates. And so you can see in both some different standards, EnerPHit is now based on climate zone, and the FIAS system is also based on location. Um, there was a time when Passive House had kind of a one size fit all requirements. So like you just had to achieve very low um, energy heating and cooling energy usage for the home, irrespective of the climate zone. And so then they required very high levels of insulation, even for a place like San Francisco or Portland, Oregon, that compared to like other parts of the country, were considered pretty mild. Um, and so now the insulation levels are a little bit more toned down, but still, significantly higher than um, code. And so, like for example, like on the far right hand side for the FIAS core prescriptive method, I put in Portland, Oregon, and a home that has 1,300 square feet and 4 bedrooms. And it's saying that if you go through the prescriptive path, your walls need to be R32. Well, a 2x6 wall, even if you blow in insulation, you're really not going to get more than like 23 or 21 out of a 2x6 wall in the cavities. And so um, you're going to need exterior insulation on top of the, filled 2x6 wall. And then really the other thing is they're saying minimum effective R value. Effective, so meaning like, it's not just cavity insulation. You're talking about, you know, um, effective. And so you're going to need some exterior insulation, and so there's different ways to do that. But this is a prescriptive, but then uh, both the PHI and FIAS pathways, there's some ways to do calculated methods, and so through energy modeling, you might be able to do some uh, trade-offs. And so what I mean by that is like, recall in the previous slides, where we're talking about crappy windows versus really good windows. Now, if you have really good windows, you might be able to really shrink back down your wall. And so, um, in the right-hand side, over here, the first line under thermal enclosure, the default is a 0.25 window. Now, if you could get a 0.15 window, which is much better, then maybe that'll dramatically shrink down, the amount of insulation you need in your walls down to maybe, gosh, I don't know, maybe you might be able to do it with R23. Um, and so then R23 would be achievable without exterior continuous insulation. So, those are some trade-offs that you might be able to do with your passive house consultant, and they can run some energy models to help guide you on kind of the most cost-effective trade-off to make. So one of the maybe most difficult elements of passive house is the air tightness requirements. Um, in the past, the passive house, you had to hit zero point 0.6. But now depending on which pathway you take and the size of your home and stuff like that, yeah, they allow up to sometimes one air changes per hour at 50 pascals, and this is like measured using a blower door. Um, Even at one, I mean that's still way tighter than the 3 to 5 air changes per hour that your standard residential energy code um, allows you to do. And so you just have to be absolutely crazy about thinking about air sealing details and air sealing um, and ensuring that the air sealing that you do is not decorative air sealing, but actually performing that. And so I've done a lot of air sealing in my life, and regrettably, sometimes, I thought I did a good job, and then when I ran the blower door and then felt around or used my thermal imaging camera to look, I see that it's still leaking, even though I already applied air sealing product to that location. And so then I have to go back and like seal it again, and then keep iteratively doing that until the places that I intend to air seal are actually sealed. And so this is one of those things, like, with Passive House, you have somebody actually coming in to do blower door testing, and so your air sealing details must perform. Another area of Passive House principle is uh, a envelope that has very few thermal bridges, and the reason for that is both there's a comfort issue. So like if you have most parts of your house be well insulated, but then like this area that's not well insulated, then if you happen to be in that area, it gets very cold and uncomfortable. So it's a comfort issue, but it's also a building durability issue. So like moisture will condense onto cold surfaces. And so if you have thermal bridges, like for example, windows, like I was saying earlier, if you have very high quality, high performance glass, but then a crappy window frame, then potentially in the wintertime, you get condensation around your window because your indoor air is warm and moist, and then it's very cold on that crappy frame. And so then all that moisture will condense onto the window frame. And so uh, during the process of uh, getting a home certified for Passive House, there will be an exercise to examine the envelope details, not only in the plans but also as executed, um, to look for thermal bridges. Um, and so typically how that thermal bridge is identified is visually. You can sometimes most of the time see them, but sometimes not. You might surprise yourself, which is why most uh, consultants will not only do a visual inspection, but they'll run around with a thermal imaging camera to look for thermal imaging using a thermal imaging camera as well. So um, some of the uh, main benefits of passive house is a improvement in durability. So like, the crazy amount of air sealing to get to a zero point 0.6 or one air change per hour. Like, why is that, really a big deal? And it's because air movements results in a lot of moisture movement. Um, Here's some work that Joe Lestibrick at Building Science Corporation did to look at how much a water in the form of moisture can be transported through a 1 inch square hole. So a 1 inch square hole is a very small hole um, in the grand scheme of things. And he did some analysis and some testing and found in the Chicago climate zone, a 1 inch square hole, you can get 95 quarts of water over the course of a season um, transported through a 1 inch square hole. That is a ton of water, and that's way more water than is needed to cause a mold problem inside a building assembly. And then that mold problem obviously leads to building durability problems and health problems. And so trying to get that air leakage down to 0.6 or 1 air change per hour it contributes a lot to building durability. So another kind of element to the passive house, having very few thermal bridges, very tight envelope, very well insulated envelope, is that if you were to lose power during a winter storm, you're able to ride out that winter storm for many, many more hours than a home that is less well air sealed and less well air insulated. And Rocky Mountain Institute did a great a modeling report to show just how much of a difference it makes. So in this simulated weather profile, shown in the gray line there, um, if you were to experience a power outage under those outdoor conditions, um, if you had a passive house, you could, you know, go for 152 hours before the indoor air temperature, which started at 68, would drop down to 40 Fahrenheit. Um, versus if you had a 1950s house, then within 8 hours, you are going to be at 40 degrees already. So this is a huge difference. Yeah, so could be this type of data could be, for you or others, maybe the compelling reason to pursue a passive house. So as I was saying a little bit earlier, that passive house in the 1970s and 90s and all the way up to um, about 2012, 2015 was really fixated on um, building homes that were super well insulated, so that like in Portland, Oregon, you would still have like R35 walls, um, and there wasn't much in the standard to allow you to deviate from that. Um, and so the problem with those kind of strict standards was that in Portland, Oregon, or San Francisco, uh, it's kind of overkill. And so then, if you were to pursue a passive house built house, you'd be spending a lot of money on insulation, and that insulation obviously comes with some embodied carbon, and so you're unnecessarily spending money and also in, use putting embodied carbon into your building, um, and not really getting much benefit out of it. And so in the kind of 2010, 2012, era, enough noise was made in the building science community that passive house standards started to change. And so the first change was FIAS in 2015 um, made a change to have the standard be adjusted based on climate zone and the size of the home. Uh, and so that's really good. And then some further adjustments were made in 2018 and 21 and 24. And that now you get that, the calculator that I showed you in a previous slide, where the heating, cooling loads and the insulation values are dependent on climate zone. Um, so there's some adjustments now, and so as a result, now it's possible to build a passive house using at lower cost than previous because, like in Portland, Oregon, you can build one and achieve passive house certification without needing quite as much insulation as um, in like 2010, for example. And so that's really good and improved and a really good improvement um, to getting more homes and more interest in passive house. So as I was saying, passive house has in both PHI and FIES, two kind of main organizations that set the passive house standards. Um, they've kind of branched out a little bit. Two kind of areas of branching out into is one is into retrofit. So having a different standard for retrofit versus new construction. And the standard is not only different, but the certification pathway is also a little bit different. The retrofit pathways allow one to um, take their time and like do the retrofit stepwise. Like you can do it like retrofit the walls, and then a year or two down the later, then retrofit the roof, and then a year or two later do the crawl space, for example. And so there's a that path allows for this kind of step down in um, energy intensity of the building. Um, and then there's also the other kind of element, which is an attention to renewable energy. So Passive House, kind of before this latest modern um, set of standards, was principally focused on making the building use as least a little energy as possible. Um, but they didn't pay much attention to the where the energy came from. So that means you could have natural gas, you could have um, no solar, but now there's standards by both PHI and FIES to give credit and uh, highlights homes that go above and beyond building a a home that's very energy efficient, but also a home that has renewable energy. And so you get credits for renewable energy. The PHI, they have the classic, which is just a home that's very energy efficient. The plus is kind of like a net zero home, where like in the course of annual, um, in the summertime you generate a lot of excess solar, and then in the wintertime you use up those credits. And so the plus, is a annual kind of net zero approach. The PHI um, premium uh, requires you to have your on-site generation be much more than your on-site energy usage. And so what that's trying to think about is, well, in the summertime, not only does your home generate a lot of solar energy, but the utility energy mix is also pretty clean because the electric utility also has a lot of utility scale solar and wind. And so the electricity mix in the summertime, when you sell a excess kilowatt hour into the grid, you're actually offsetting a relatively clean kilowatt hour in the summertime. And then in the wintertime, when your solar is not generating much energy and the utility is not generating much energy from their solar either, then the utility needs to feed your house uh, uh, makeup electricity, and that makeup electricity needs to come from non-renewable sources, and so like typically natural gas power plants. And so then that is a relatively dirty kilowatt hour that you're consuming in November, December, January, February. And so the premium tier kind of recognizes that, and uh, the way that it considers that is, okay, well, you need to generate a lot more of those clean kilowatt hours in the summertime in order to actually successfully offset those dirty kilowatt hours you purchase in the wintertime. Um, so that's kind of the difference between plus and premium. On the FIA side, the zero is the FIA Zero Performance and Zero Revive are ones that consider renewable energy. Um, I believe that zero is more of an annual net zero means of doing energy in computation. And then the Revive is the retrofit standard, similar to the PHI EnerFit. So another kind of cool thing about Passive House is that if you get your home Passive House certified, then it really encompasses many other standards. So it encompasses the DOE Zero Energy Ready Homes program, the WaterSense program, the EPA Indoor Air Plus program, and then also the Energy Star program. And so oftentimes at the federal and state level, you get some tax breaks or credits for building a home that meets these programs requirements. And so if you build to Passive House certification standard, then you automatically kind of check all these other boxes, and that means that a Passive House certified home can qualify for quite a few of these incentive dollars, and these incentive dollars can be used to kind of offset the certification cost or some of the additional cost to meet Passive House, such as offsetting the cost of the ERV, for example, or offsetting the cost of incremental cost for better windows. I don't care how you do the math or the accounting, but there are incentives, and these incentives have certainly been at least lucrative enough that it spurred a growth in interest in Passive House as a home certification. So now, one of the things to think about is that uh, only about 1% of the building stock is new construction that gets built each year. So for every year, there's still 99% of the existing homes that are not even to new construction standard. And so um, it, that means that the majority of the opportunities to the majority to reduce energy in a building is through retrofitting, and retrofitting a home to Passive House standard is perhaps a very good option, but it's something that you have to kind of um, one, see if the home is a good candidate for that. So, like, does it have good bones? Like, will you have to do major structural remediation and termite remediation and rot remediation in order to even start the process? If so, then maybe that home is not a good candidate. But, if it's in relatively, good shape, it's just drafty and poorly insulated, then, that may be a good candidate to engage in the process of retrofitting this existing home to Passive House certification standards. Um, Another thing to start with is you really have to consciously identify that as a goal. The reason why is that if you don't go through, home remodeling and home repairs with that goal in mind, inevitably you'll end up missing opportunities to um, get your house to that Passive House standard. Um, what I mean, some examples of that, it would be like, oh well, the furnace goes out, and then you're interested in replacing it with a heat pump. Well, if you size the heat pump to the current load of the house, you might end up with, a 3 or even, God forbid, a 5-ton heat pump. Um, but then if you pay and purchase that heat pump at 3 to 5 tons, then you're locked in to that 3 to 5 ton heat pump. And if you're going to then do subsequent work that brings down the heating cooling load of the house dramatically, potentially down to 1 ton, then now you're stuck with this 3 to 5 ton heat pump. And so um, by conscientiously identifying that, yeah, I want to get my house's load down and reduced down by, 75 or 85%, then that really kind of shapes kind of the decision making you do. Like, even if your HVAC contractor, tells you that you need a 3 ton heat pump, you can have that conversation with them and say, no, no, well, I will in the next 1 to 2 years, do a bunch of envelope work on my house or hire somebody to do that work and reduce my loads down to needing only like a 1.5 ton heat pump. And so then help the HVAC contractor understand why you would want a 1.5 ton heat pump. Um, so that's the and that also kind of speaks to the sequencing of the project intelligently. So like you're not purchasing um, things and doing things out of sequence. So another kind of good example of that is like, okay, well, um, air sealing a home to make it more energy efficient. That's very important and worthwhile work to do. But if your windows are in really bad shape, like you have aluminum, you know, windows, double pane, and that may not even have any gas or low E in it, then it really doesn't make much sense to carefully air seal the rough opening to window gap in those crappy windows, because then you're going to need to tear them out, in order to achieve your passive house goal. And so, sequence the project and think and don't do stupid things that you're going to end up having to like redo later um, by sequencing things incorrectly. Um, and one of the ways that to sequence things in a retrofit project as logically and efficiently as possible is one way to do that is to hire a passive house consultant who can kind of guide you through the sequencing. Um, but even then, like whenever you hire a contractor to do this work, you have to be very careful about the contractor you hire because the quality of the workmanship matters a lot in a passive house, and not many contractors know or have kind of the default quality to high enough to meet the quality to achieve a home that will be successful at getting the passive house certification. And so one of the ways to get quality without, emptying your bank account is to do some of the work yourself. And so I met most of the retrofit projects that have successfully met the passive house retrofit certification. The homeowner has done a lot of the work themselves. And so that's something to consider. So, in conclusion, the majority of the opportunities to reduce energy in the building stock is in the retrofit kind of area, and so the PHI and FIAS pathways for retrofit um, really should be used a lot more because that's where the opportunity is. And as you saw in the previous slides, Passive House is really simply a collection of well-executed best practices that really any good home should be doing anyways. Like, why wouldn't you want a home that, has filtered, energy recovered fresh air? Why wouldn't you want a home that's really airtight so that, wildfire smoke doesn't come through the gaps and cracks? Of course, like everybody would want a home like that. So, if you just execute these best practices, then and you do it really well, you you're pretty much at Passive House. Um, and every year the number of homes that are achieving Passive House certification is increasing dramatically. You'll see in the next slide that it's an exponential growth, and this has really resulted in this knowledge on like the best practices, best bang for the buck products, and know-how to achieve all the goals, whether it be durability, health, resiliency, comfort, and energy efficiency, to be able to achieve this, all these goals while still being cost effective. Um, the knowledge on how to do this is growing every day. And so here's data from PHI showing that, wow, we've really gained a lot of ground in the world of Passive House. And with that, that's all I have for Passive House. And I do want to do a plug for next Green Energy series, which is on February 1st, and it's going to be on electrical panel upgrades. And in this Green Energy series, we're going to talk about arc fault circuit interrupter, combination arc fault and ground fault circuit interrupters, and whether you need to upgrade your service or just upgrade your panel. Um, and then also discuss things like what you should do to future-proof your house, and look into like if you look into things like circuit sharing, and kind of like if you don't want to do a full panel upgrade, what kind of options do you have? Your panel is fully occupied already, but yet you still want to add like a induction cooktop or add an EV charger, and there's just simply no space. So what are some of the options associated with that? We're going to cover all that on February 1st. So with that, I will look at try to find the question and answer and see if there are any. Let's see. How do I? Give me 1 second. Okay, there. Chat or Q&A. Okay. We have some questions. Okay, is your position at risk with the incoming administration? Is there proposals to delete Department of Energy? No, that's not going to happen. Okay, another question. What do you think of well-designed window quilts? And there's a link to a video. Okay. I'm not going to click on that video right now. But window quilt. So I'm assuming that's some sort of like insulated window shade. Um, and those are typically, quite good. You do have to be careful with condensation on the window sill area when you have insulated window shades. And the reason for that is because um, insulated window shades on the interior of the window will really significantly reduce the amount of heat leaving the window, but it won't really stop any of the indoor air or humidity from reaching those cold condensing surfaces, whether it be the window frame or the glass. And so indoor humidity will still reach those cold condensing surfaces. So if you use insulated window shades, sometimes it may be necessary to actually close the window shade, leaving the bottom 1 inch or 1.5 inch of the window sill not insulated by the interior shade. And that allows just enough heat to warm up that window sill space to prevent condensation. Um, Something to think about. Another question, how does solar energy, passive and PV fit into Passive House? Yeah, so um, the energy modeling in a involved in the Passive House project will look at your glazing positions and glazing shading. So if you have exterior shades that will shade the windows at certain um, times of the year with the sun angle, it'll take into those things into account. Um, there are certain metrics for the number of hours that a home can be allowed to be overheated beyond the um, comfort band. And so you may have to, adjust the location and size or shading of those windows in order to meet the hour of the allowable hours of overheating. And so that kind of fits into the optimizing for passive solar design. Um, for the active photovoltaic um, element, as I said in the um, different flavors of the PHI and FIAS um, standards, the base uh, versions of the standard don't necessarily do much accounting for photovoltaics, but there are standards that give credit for the photovoltaics, and in fact, you cannot achieve those more difficult or premium standards without uh, photovoltaic or renewables, and so that's how that gets dovetailed into the passive house standards. Here's another question. Thank you, Edward, for another one of your thoughtful presentations. Okay, yep. I really do enjoy giving these. Um, what about outlets? Is there a quick and dirty fix for intrusion? Um, so electrical outlets, d depends on the outlets. If it's a metal box, typically metal electrical boxes have enough holes in the back or the side of the outlets for you to actually get a spray foam gun and just put the tip of the spray foam gun right into that hole and then just shoot a bunch of foam into the outlets. Um, and then you can also caulk around the perimeter of the outlets between the drywall and the outlet to um, really significantly reduce the air leakage without, and you can do both the perimeter and also put foam that expands outside of the outlets and do both of these things without getting that much foam inside that electrical box, which is not allowed. There's electrical code that does not allow you to have insulation foam or caulking inside that displaces the what's it called, the cubic inches of space inside the electrical box. Um, Now, will those measures be enough to get your house, existing home, to meet the passive house certifications? Eh, maybe, maybe not. Um, Typically, most of the existing homes that are retrofitted to meet the passive house standards, those are involve a lot more than just foaming outlets and putting some weather stripping around doors and windows. Those are typically, they require the level of like a gut remodel, as where drywall is being taken down and then like your top plates and bottom plates and penetrations are comprehensively air sealed. And so if you take down the drywall, then you don't need to be spraying spray foam through little tiny holes in the back of an outlet. Um, you can, put caulking or there. The most kind of common way that outlets are air sealed is with putty pads, and they're these like 6 inch by 6 inch pads of putty that you can wrap the outlet in, and that forms a really good air seal. So it's something that you can really only do with the drywall removed. But if you're going to pursue a passive house retrofit certification, maybe something that you have the opportunity to do. Well, that seems to be the all the questions. And with that, I hope you guys have a great rest of your Saturday and the rest of your weekend. And I hope to see some of you back on February 1st for the next Green Energy Series. Also, pay attention and go look on Eventbrite, Solar Oregon for other events that are, available between now and February 1st. And yeah, that's all I have. And thank you for attending this one.